Hello everyone, welcome to my YouTube channel Know About Embedded System. So in today's video we will understand two important things with respect to CAN protocol. One is called bit stuffing. What do you mean by bit stuffing and why the bit stuffing we will be using in a CAN protocol? That's the first thing. And second thing, we will also learn what is NRZ coding. So there are two things we're going to learn in today's video. One is bit stuffing and one is NRZ coding in a CAN protocol. So these two things we will study in this video. So before starting the video, if you are a new viewer to my channel, kindly subscribe my YouTube channel and gain the knowledge on embedded system. Let us start the video. NRZ coding and bit stuffing in CAN protocol. In today, we're going to use something called as NRZ coding. CAN protocol uses something called as NRZ coding to represent its bits on the CAN bus. Here you can see what do you mean by NRZ coding, that I'll explain later. I'll show you what do you mean by NRZ coding with respect to the waveform here. You can see this is my input bits. These input bits are represented like 1, 0, 1, 1, something like that. And NRZ coding, the full form of NRZ coding is non-return to 0. What is the full form of NRZ? NRZ stands for non-return to 0, and we are not using a 0 voltage, or we will not return to 0 voltage when we are representing our signals. This is called as NRZ coding. So when you see here input bits, and this is my NRZ coding, you see the voltage level is monitored. Voltage is represented from 2.5 to 1.5 voltage. 1 is represented by 2.5, 0 is represented by 1.5. Drawbacks also that we will discuss. So what is this NRZ coding? Let us understand the definition. We know that already CAN protocol uses NRZ coding, that stands for non-return to 0. What do you mean by this non-return to 0? Non-return to 0 means CAN protocol uses NRZ coding, which is going to your CAN protocol directly, it is going to map your zeros and ones using NRZ coding. This is one of the coding technology to transmit the bits. Okay, so CAN protocol uses this NRZ coding directly to map the bits. Now, second point, if you observe here, what do you mean by NRZ coding? NRZ coding means it is when the signal remains its constant state entire the total period of your signal. So if you observe here what it says, so this is my total signal, and signal remains as it is. So the signal level will be maintained constant throughout your total time period. If you observe here, so throughout signal representation, throughout my signal time period, your CAN signal will be having constant voltage. That is called as NR. We never go to 0 and we never return to 0. That is what he is telling. The signal remains at its state for entire period without returning to neutral or without returning to 0 volt. This type of coding methods are called as NRZ coding. NRZ coding means the signal, your CAN signal will remain with a constant voltage, or it will maintain the constant voltage throughout your total time period of your signal. This is called as NRZ coding. And after the third point, if you see here, in NRZ coding, we know that already we're going to use something called as dominant bit and recessive bit. Dominant means logical 0, recessive means logical 1. With the help of logical zeros and ones, we're going to represent our bits in a NRZ coding. So why we are going to use NRZ coding? NRZ coding is very easiest way and a very efficient way to transmit the bits. That's why we're going to use NRZ coding in our CAN protocol. I hope you are understanding what you mean by NRZ coding. So now there is one small drawback is there in NRZ coding. What is that? We will see. The major drawback with the NRZ coding, they are not self-clocking. NRZ coding, whatever we have studied in the previous slide, they are not self-clocking. Self-clocking means they are depending upon our input signals. They are not they are not generated from self, or they do not have any clock at all. Okay, so because of this, you can see here, because they are not self-clock mechanism, they are not following any self-clock mechanism, and it is going to create a synchronization problem in the receiver and transmitter. For example, for a longer sequence of identical bits, which will be occurring more than 5, that is going to create a signal with a flat. So what do you mean by that? If you're representing signals like this, signal will appear like a constant straight line when you're using NRZ coding. But according to our CAN principle, the CAN principle says that periodically the signal should be, it should change its value, or it should change, the signal should periodically, signal should change. Signal level should change. 0 to 1, 1 to 0, 0 to 1, and 1 to 0. Like this, the signal should change its state continuously. At least for 5 bits, once it has to change the signal. In order to keep your transmitter and receiver in a proper synchronized way, signal should change its state 0 to high, and 0 to low, and low to 0. High to 0, high to low, and low to high. But in case of this scenario, you can see when I'm transmitting continuous number of ones, there is no signal change at all. That is what the drawback of NRZ coding. So the major drawback of NRZ coding, they are not self-clocked. That means they are depending upon input bits. And whenever you're transmitting the bits like this continuous number of zeros and continuous number of ones, the signal will appear like a flat signal. The signal will be appearing like a flat signal, which is going to cause a receiver and transmitter synchronization issue. There might be a problem. There might be a possibility of losing the synchronization between transmitter and receiver. So why it will happen? In our CAN protocol mechanism, it is properly defined that periodically signal should change its state. Either the bits should change, or if not, we have to change it. We have to change it by some other mechanism, or else the receiver and transmitter will lose the synchronization. So engineers and scientists, they come up with a bit stuffing mechanism. What is this bit stuffing mechanism? Says that bit stuffing says like this: for every 5 consecutive bits, for every 5 consecutive bits of the same polarity, the sender automatically inserts a complementary bit or opposite polarity bit. This process is called as bit stuffing. For every 5 consecutive bits of the same polarity, the sender or a transmitter will insert an opposite polarity bit during the transmission. So this is called as bit stuffing. So we have to use NRZ coding along with the bit stuffing. So now we will see in this slide what is bit stuffing and how bit stuffing will happen. That part we will understand. What do you mean by bit stuffing? Just already we have discussed. Bit stuffing means it is a mechanism of inserting an opposite polarity bit whenever you're transmitting number of zeros and number of ones more than 5. A mechanism where transmitter will insert an opposite polarity bit after 5 consecutive transmission of same value. Nothing but continuous number of zeros and continuous ones. When you transmit, we are going to add, or we are going to insert an opposite polarity bit. This process is called as bit stuffing. Why we have to follow this method? We have to follow this method to keep receiver and transmitter in a proper synchronized way, and to prevent the bit stuffing error. I hope you are clear. So why we have to do bit stuffing? To keep the synchronization proper, or to ensure the synchronization is proper, and to prevent the errors. So this is going to happen in a transmitter side. Stuffing will happen in transmitter side, and destuffing also will happen in the receiver side. On the other hand, receiver will remove the stuffed bit that is called as a destuffing to recover the original data and to ensure the reliable communication is happening on the bus. So bit stuffing will happen in the transmitter side, bit destuffing will happen in receiver side. Let us consider one example here. So in this example, I have a continuous number of ones and a continuous number of zeros are represented. This is before transmission. You can see here, I have a signal and this signal is before transmission. Okay, now what will happen during the after transmission? Now you can see when you transmit the data, according to our bit stuffing rule, what bit stuffing rule says, every 5 bits, for every 5 consecutive bits, an opposite polarity will be added, is called as bit stuffing. Now if you observe here, every 5 bits, okay, this is my 5 bits, 1, 2, 3, 4, 5, opposite polarity bit is added. This is called bit stuffing. So this is a stuffed bit, this is a stuffed bit, this is a stuffed bit, and it goes on like that. For every 5 consecutive bits of zeros and 5 consecutive bits of ones, opposite polarity bit added. So it should be continuous zeros or continuous number of ones. You can see here I'm getting continuous number of zeros, and here continuous number of ones, continuous number of ones, like that. This process is called as bit stuffing. So this is after transmission, and I have one more use case here. After destuffing, so we have a before transmission case and after transmission case, and finally I have after destuffing. So after destuffing, your original data will be recovered. The stuffed bit will be removed. When you receive the data, so it is the stuffed bit, whatever we have used a stuffed bit, that stuffed bit will be removed and the original data will be recovered. So this process is called as stuffing and destuffing, and this, with the help of this bit stuffing, we will be having the network in a properly synchronized way, and we can also ensure that the communication is happening without error, and properly receiver and transmitter both are in a synchronized way. So I hope you are clear with the two topics. One is a bit stuffing and one is NRZ coding. So if you feel this video is an informative video, please click on like button and subscribe my YouTube channel.